Hi guys, and today what I've got for you here is a little video demonstration on this technique we call completing the square. So if you are an advanced middle school algebra student or a high school algebra student especially, or even if you're a pre-calc student or a calculus level student who needs to review this method, this video is for you. So I remember even when I was learning this for the first time that a lot of times seeing it in symbolic form, just the algebraic steps, it's a little hard to grasp what you're doing. Why is it called completing the square? What's really going on here? And it's a little hard to remember and then understand when to use it and what it's for. So to start off, I'm going to address the question as to what is completing the square. Well, a lot of times in math we come across expressions that are of a quadratic form, like this: ax squared plus bx plus c, where these letters a, b, and c represent numbers or coefficients, and the letter x represents our variable. So completing the square would be a process or a technique we would use to change an expression like this into a form where the variable x only appears one time. So for example, with quadratic functions, where we have like the standard form of a parabola here, we might want to change it into what's called graphing form or vertex form, which is oftentimes written as a times x minus h quantity squared plus k. And in this form you'll notice that the variable x only appears one time. So the reason that that's useful is because in this form that's called graphing form or vertex form, there's a lot of good information we can get out of this form that helps us actually draw the picture of the graph. So there's a lot of other places where this is useful, including the graphing form of different conic sections, which I'll address later on at the end of the video. But what we're going to do is demonstrate how to complete the square in general using an area model or a visual approach that will hopefully demonstrate why this technique works, why it's called completing the square, and hopefully help you understand what's going on a little bit better. So to start off, for the purposes of the visual demonstration, I'm going to use a slightly simplified quadratic expression, x squared plus bx plus c, where the coefficient or the number in front of the x squared term is 1. I'm just doing this so that I can draw the picture nicely, but after you see the picture, hopefully if you understand it a little bit better, it's easy to do, or easier to solve problems where this number out in front isn't 1. There's just 1 or 2 extra steps which I'll show later on. So to start off, our step 1 is going to be to represent this expression in terms of area. So what we've got to start off is literally a square of side length x, which is going to have area x squared, right? And then our second piece is going to be to represent this b by x rectangle, where the width is b and the height is x. And our last piece is going to be this component c, which will represent with a small rectangle of width c and height 1, which is going to have area c. As we know, the area of a rectangle is width times height, c times 1. Same thing for this one, it's going to be area b times x. And there we go. Step 1, we've got our quadratic expression represented in terms of area, where right here we've actually got a big rectangle of height x and width x plus b, and then over here on the side we've got our leftover c times 1 rectangle. So the reason it's called completing the square is because what we're going to try and do is reconfigure this rectangle right here into a form where it actually looks like a square, where all the x terms are gathered into one piece, and we might end up with some leftover stuff on the side that won't have any x terms in it. So our second step in order to get there is to try and reconfigure this rectangle into something that looks more like a square, where the side lengths are the same. So in order to do that, what we can do is cut this b by x rectangle into 2 pieces, which is going to give us 2 rectangles of width b divided by 2 and height x. So in the second step, I'm going to redraw this where we leave one of these pieces, b over 2 by x rectangles, right here, and we're going to take the second one and we're going to move it right underneath and realign the height with this width x and it'll start looking a little bit more like a square. So we've got our x by x squared still, with area x squared, and I'm going to leave one of those rectangles with width b over 2 and height x right there, and then I'm going to take the second one and put it right down here on the bottom left, and now it's got height b over 2 and it still has width x. And then of course we've got our little leftover piece c by 1 with area c. Now, as you can see, we're getting a lot closer to a square, and that's now it may be a little more obvious why we call it completing the square, because all we've got left is this little corner that we're missing in order to have a complete square. And if you look what we've got, since these are rectangles, we know that this length is also going to be b over 2, right here, b over 2, and same with this length right here, that's going to be b over 2. So if we fill in the rest of the square, the area of that little corner we're missing is going to be a square of side length b over 2, which would have area b over 2 squared. But the issue is we just added in some extra area out of nowhere. So in order to maintain the equality, we've got to make sure we subtract that same area that we just added in order to make this square. And I'm going to use blue to represent negative area here. And we're going to add in another square with negative area and the same dimensions, b over 2 by b over 2, which would have area b over 2 squared. Now if we just look at what we've got represented here and try to draw it out in one sum, we've got a square whose width is x plus b over 2, which we could represent as x plus b over 2 quantity squared, plus our original c by 1 rectangle, this c right here is still there, and then in order to maintain the equality we had to subtract a b over 2 squared. So there we go, we've taken our quadratic expression of this form, x squared plus bx plus c, and changed it into a form where the variable x only appears one time. And now to demonstrate this, I'll just use a simple example right here with a quadratic expression x squared plus 2x plus 2. Now that's really close to a perfect square, but what we're going to do to summarize the algebraic steps, we took the coefficient of our linear term and divided it by 2, and that's what goes inside this quadratic piece right here. So we're going to have an x plus 2 divided by 2 is 1, so we'll have a 1 in there, and we'll square that. And then we've got our original 2, which is represented in general by that c. And then we just added in an extra b over 2 into the area, b over 2 squared to be exact. So we need to subtract this b over 2 squared, and 2 over 2 was 1, and 1 squared is 1. So we're just going to subtract 1, and that would equal x plus 1 squared plus 1. So there you have it, there's an example, and if you wanted to know what would go on if this coefficient wasn't 1, all we'd have is, in general again with the letters representing our coefficients, we would just need one additional first step to factor out that a, and we'd be left with a couple of fractions on the inside here. But now what's on the inside of the parentheses looks a lot like this one with a couple of fractions, and we could carry out the same kind of technique where we take this coefficient divided by 2, square it and put it right here, and then make sure we subtract that same term on the outside. So there you have it, that's completing the square. And if you're wondering why we would want to do this, why is it useful, well, there's a lot of different scenarios. So first of all, as I mentioned at the beginning, with the graphing form of a parabola, we end up having to go from standard form to graphing form or vertex form, and in order to do that we need to complete the square. Also, completing the square is an essential step in deriving the quadratic formula, which is another super useful tool for getting information about a quadratic function that we need in order to draw the graph. But it also comes up with all the other conic sections. So for example, with the graphing form of a circle, it looks something like this. Make sure you can see that with the x minus h squared plus y minus k squared equals r squared. This may or may not look familiar, but that's the graphing form of a circle. Where look, we've got an x minus h squared term and a y minus k squared term. And in order to get those, we would have to complete the square, because oftentimes the expression is not just going to be given to you in this nice graphing form. The same goes for ellipses and hyperbolas. They have these x minus h quantity squared terms and this y minus k quantity squared term in them, and it takes completing the square in order to get it in the graphing form. Also, if you're a calculus student, and this has come up in my coursework as a college math major, you need completing the square to carry out some complicated integrals. So if you've never taken calculus or never seen this and the notation doesn't make any sense, that's totally okay, you can disregard this. But if you're a calculus student, you might recognize an integral that looks something like this. Plus x squared dx. And if you wanted to go about computing an integral like this, the technique you actually have to use is completing the square with this quadratic term underneath the square root. And after completing the square, we can use something like u substitution, which is something you learn early on when you're learning how to integrate things like this. But if you don't recognize that you need to complete the square, or you don't remember how to complete the square, this integral can be pretty complicated and you can get stuck really fast. So that's a place where completing the square has come up even in my coursework as a college level math major. So I hope that helped, getting a little visual demonstration of completing the square, why it works, why it's called completing the square, and what's going on behind the scenes, and simplified some of the algebraic steps, and will help you carry it out in lots of different scenarios and problems. So if you've got any questions, feel free to leave them in the comments below, and I'll get to those answers as best I can. And I hope that helped. Thanks.